We did all of that math to cancel everything out to determine the pH was the same as our pKa. We're going to use that information to talk about a buffer solution. Who has heard of a buffer solution at all? Oh, good, a few of you. All right, we like buffer solutions. What the heck is it? It is a solution that resists pH change because you are going to be neutralizing acid that you add or base that you add. And you'll get to see this when we do it in lab, titrating a polyprotic acid. So what you're going to do is you're going to make one using conjugate pairs. So if you're going to use a weak acid, you would also use its conjugate base. You mix them together. Or you can mix a weak base with its conjugate acid. Note, you cannot make buffers with strong solutions. You cannot make a buffer solution with a strong acid or a strong base. They have to only partially ionize. You must start with a weak acid or a weak base and mix it with its appropriate conjugate. So in order to do this, you pick the right products, starting reactants if you prefer. You have to have a significant amount of each. So like what we just did on the first page, a buffer is going to be most effective if you have equal concentrations of the acid and its conjugate base, or equal concentrations of the base and its conjugate acid. It's not going to be very effective if you have a tenth of one versus the other. So you need to have significant amounts, preferably equal amounts of both, to make it most effective. So you want, within the buffer to work, your ratio, in this case I did it with an acid, of your conjugate base to your acid needs to be between 0.1 and 10. So you don't want to have any more than 10 times more of one than the other, or it breaks the system. When these criteria are met, the buffer is going to work over a range of 2 pH units. If you think about that, it makes sense, because you're going 2 orders of magnitude on your ratio scale, which corresponds to 2 pH units, if you prefer to think of it that way. If you don't, if that just went over your head, don't worry about it. So what you need to know is you need the concentration of each component. Most commonly, these are acids and their conjugate bases, so if I say that, no, you can use the opposite if you prefer, but generally you're going to use the acid and the conjugate base. So each component needs to be greater, the concentration, than your Ka by at least 100. Why does that matter?
Extra small.
Because you can use extra small. Otherwise you can't use extra small. Because if it's greater, then M over K is always going to be greater than 100, so you can use extra small. Makes math much easier. We like extra small. Now, Another way to talk about a buffer solution is called the common ion effect. And that is where you have two substances. And guess what? They share a common ion. Like the example we did on the first page, acetic acid and sodium acetate. They both have acetate in common in solution. So when that happens, when they have the common ion, you're going to have a decrease in the ionization of the weak acid or the weak base, which is what we just proved in the previous example. Does everybody have these blanks? Okay, I'm going to flip back here. Because let's think about Le Chatelier's principle here. Le Chatelier's principle says we're going to shift in the direction to minimize equilibrium. If we start with this and we have a whole bunch of this, are we going to make many products? Not really. Are we going to make many reactants? Not really. And that's the point. So it's channeling the power of Le Chatelier's principle to resist pH change. So I am going to give you the Henderson-Hasselbalch equation. This is the last thing I'm going to do today. I'm not going to do any examples with it. We'll pick up here on Wednesday. So the Henderson-Hasselbalch equation says, first of all, you're going to love me for this. It is a shorter way to determine the pH of buffer solutions. So if you hate ice tables, it's your lucky day. You can use the Henderson-Hasselbalch equation to do that. Or if you don't like that and you're comfortable doing ice tables, you can do an ice table and you'll get the same answer. But it says pH of the solution that has a buffer equals pKa plus the log of your ratio of base to acid. And you can only use this when molarity over Ka is greater than 100, so that you're able to use X is small. X is small. Most people find that this makes their life simpler. If you hate it, use an ice table. It's fine.